Welcome to the Optimum Monkey See breakout session. Over the last few years, the ConnectIQ team has been rewriting the Monkey See build tools from scratch to create a more modern and advanced toolchain. This breakout session will cover the core features of the improved build system. First, a little about me. My name is Mary Ann. I have a master's in computer science from the University of Kansas. I joined the ConnectIQ tools team back in 2016. I am the Monkey See compiler project engineer, which just means I write more design than code these days. And finally, I enjoy playing with my dog Poco, who is pictured here on this slide. Monkey See. If it looks familiar and non-threatening, then you guessed it. That's the point. Monkey See is the language you didn't know you already knew. It derives heavily from popular languages like C, Java, JavaScript, Ruby, and others. Unlike statically typed languages, Monkey See is duck-typed, which is the concept of if it walks like a duck and quacks like a duck, it must be a duck. In addition to being duck-typed, Monkey See is a message pass language. So when a symbol is invoked, the virtual machine executes a lookup operation at runtime to find the symbol. The search starts the narrowest scope and seeks outward. Given this example, invoking the instance method A on a child object would execute 3 simple print statements. However, 2 of them would require runtime lookups. To print the string, "This is B," several scope searches would be required. First, a search of the child instance. Next, a search of the superclass, toybox.lang.object. And finally, a search of the module parent, which is where we would find the symbol B. To print the string, "This is C," we would need to go one step further in our search, where we would also need to look in the module parent's global namespace. As you might have guessed, this runtime lookup can be quite expensive, given that we could potentially search the entire object's inheritance structure and the module hierarchy before it will eventually find the symbol you're looking for, a symbol that could be accessed many times. Luckily, Monkey See has the bling operator, which directs runtime to jump straight to the global namespace to begin its search. While this may improve runtime performance in some scenarios, it will not solve everything. There's always room for improvement. And given that teaser, I'll now do a quick overview of the first part of this breakout session, which will cover monkey types, a feature that was previewed in 2020. I'm going to talk about the original goals of the type system. Then I'll go into the different types at your disposal and the different levels of type checking. And finally, I'll discuss applying types to your ConnectIQ applications. There are many benefits to a dynamic language. However, a type system can also offer a ton of advantages, which range from just avoiding simple coding errors to providing a compiler with enough information to perform analysis it couldn't have done otherwise. Gradual typing provides the benefits of both static and dynamic type checking in a single language by allowing the programmer to control whether a portion of the program is type checked at compile time or runtime. The monkey type system is a gradual type system that gives you the ability to add compile time type checking to your Monkey See code. We had 3 main goals in mind for monkey types. First, we wanted to ensure compatibility. Breaking changes to the Monkey See language would have required rework to thousands of apps. Monkey types extends the Monkey See grammar, but avoids structural changes when possible. Monkey types is also designed to not rely on additional runtime information. Because of this, you can use monkey types for apps that run on all ConnectIQ compatible devices. Second, we wanted to maintain our reputation for ease of use. We want the experience of writing Monkey See to be almost like déjà vu. Likewise, monkey types borrows heavily from Kotlin, Swift, and TypeScript in its design. Finally, we wanted the inherent flexibility of a gradual type system. With monkey types, there's some wiggle room between an app without any type scaffolding and an app that is strictly typed. You choose your own adventure. While monkey types allows you to add type scaffolding to your Monkey See code, the type system allows for a lot more than just associating variables with classes. There are several types at your disposal. First is the any type. Variables, function arguments, or function return values that do not have types bound to them are bound to the any type. The any type can be anything, including nothing. Values of type any follow the traditional duck type rules of Monkey See. To bind any to a value, simply do not add the as clause to its declaration. There is no keyword to bind any to a value. The void type is only for function return values. It communicates that a function does not allow a return value and that a function should not expect a return value by calling this function. Concrete types refer to declared classes in the application's namespace. If a value is bound to a concrete type, it will accept values of that class or any class derived from it. Polytypes allow for the concatenation of multiple types into a single type. This allows for the type system to model the duck type nature of monkey see. To create a polytype, you simply use the OR clause when defining your type. If a value is bound to a polytype, it will accept a value whose type is bound to one of the types within the polytype, or a value bound to a polytype whose types are within the definition of the destination type. An interface type requires a class to contain a set of member declarations. The members can be member variables and/or functions. Classes are not required to decorate themselves as implementing an interface. Simply implementing all the members is sufficient. This allows anonymous interfaces to be defined within function arguments. The monkey see language has two native container types, array and dictionary. While the monkey type system does not support generics, it does allow for the developer to bind a type to the value type of an array or the key and value types of a dictionary. Container types only match other container types if both the container key and value types match. Currently, monkey types does not infer container types. This means you will need to declare your containers as you can see in the example here. A common pattern in monkey see is to use an option dictionary as an argument. Since monkey see does not support polymorphic functions, this pattern allows for extensible APIs. Monkey types allows modeling an options dictionary by binding key literals to types. If a dictionary is declined inline, the compiler will track the types bound to the values and then type check to see if all the value types match. It will not require all keys to be provided, and it will not error if additional keys are added. Enumerations can now be named types by appending a name to the declaration. Enumeration values will be bound to both their enumeration type as well as their value type. The object class of the toybox.lang module, which is the root object for the monkey see class hierarchy that all classes extend, contains the function method. This function can be used to create toybox.lang.method callback objects, which represent a function that can be used as an argument to another function. The callback type allows you to model a method object and type check its parameters and return value. Finally, the monkey type system treats null as its own unique type. More importantly, explicit type scaffolding is required if null is an allowed value. A value bound to a concrete type will not implicitly accept null. The question mark can be used with single type declarations to make it a null accepting polytype. The type checker can be executed at 3 different levels based on your level of comfort with ambiguity. At the gradual level, type match failures are marked as errors, but ambiguity is ignored. At the informative level, type match failures are marked as errors, and ambiguity is marked as a warning. At the strict level, type match failures and ambiguity are marked as errors. Compiling a codebase with ambiguity muted can find many, but not all type errors, while more aggressive type checking, which errs on ambiguity, would require adding type scaffolding throughout the entire code set. Monkey types is designed to allow you to build towards strict type checking, while still adding value if you don't. Of course, you can always turn off type checking entirely if you prefer. Now, let's discuss how to apply types to your code. Up until now, we have been exploring explicit type scaffolding. While this makes for very readable and precise code, it can add lots of boilerplate to implementation. Unlike with class instance variables, the monkey type system will infer a type of a local variable by tracking assignments within a function. The type inference will follow through branches. If the type is unclear based on which branch is taken, the type system will make a polytype of the options until the next assignment. In this example, when we get to the return statement, X is either null or true based on which code path was taken. The type system is intelligent enough to follow these branches and track X's type through to the return statement. When a value has a known type definition, the type checker will validate if method calls are allowed. Notice here that by assigning local X to an instance of class A, the type checker can check that foobar isn't a member of class A. This is different from undefined symbol checking, which would only be able to determine if a symbol did not exist anywhere within the application's namespace. Member variables are bound to type any by default. Unlike local variables, member variables are not type inferenced based on assignment. Adding type scaffolding to your member variables will allow for stronger type checking. Likewise, if you explicitly bind variables to a type, you must either initialize the variable or allow it to be null. This means module variables either need to be initialized at their declaration or allow for the null type. Similarly, class members must be initialized at their declaration within the constructor or allow for the null type. With container types, it is possible to bind a type to an initialized value. This limits what can be assigned to the container. In this example, we can only assign strings to the value represented by A. But the local A itself is of type any and can be assigned to null at the end of the function. I'll note that binding to a type with the as clause at the container declaration is different than casting a value. When you add a type to an array or dictionary declaration, the type checker will validate all assignments to the container. If you apply the as clause to the local, it is a typecast. While the local in the example can be assigned to the null value, the member variable cannot be. As I just mentioned, the as keyword can also be used in an expression to typecast a value to another type. This can be useful if the type is not clear to the type system. For example, in this onUpdate function, the type checker can detect we are calling the view classes findDrawableById, which returns a value of type watchUI.drawable. However, drawable does not have a function named setText. That belongs to watchUI.text, which extends drawable. We know that the view is a text object, so we can use typecasting to make that clear to the type checker. Any function parameter without a bound type will be of type any. The ambiguity of the parameter will percolate to any member it interacts with in an expression. Just a little ambiguity can obstruct type checking. Take this example, where a function has a result check, but does not have an argument type for A. Because A is of type any, the type checker can't make any determination on any of its members, and by proxy, the monkey type system can't make a determination on the results of accessing these members. This code is legal at the gradual and informative type checking levels. However, to be valid at the strict level, the argument A would need to be bound to a type. When extending classes, the monkey type system will use the following rules. If you extend a function from a parent with the same number of arguments, but do not add type scaffolding, the types for the arguments and return value will be transferred verbatim from the parent implementation. If you extend a function from a parent with the same number of arguments and add type scaffolding, you must match the number of arguments and type scaffolding exactly, or the compiler will error. This allows for existing monkey C code that extends toybox types to easily take advantage of type checking without having to add any type scaffolding. In languages like Java, an object's type is assumed to be whatever it was declared to be. This can lead to some very redundant casting or creating lots of unnecessary locals to communicate to the compiler that something isn't what it was declared to be. For example, when I compile this code, I would get a message saying I was attempting to pass a polytype of number or null to a function that expects a number. The compiler is letting me know that I am not handling the possibility of a null value. To fix this, I could use a typecast, but does that really fix the fundamental issue? The null reference has been coined by its creator as his billion-dollar mistake. The problem isn't the null value itself. It is the implicit nullability of all object references, as is the case for many strictly typed languages such as Java. The high price tag comes from the constant potential for null pointer exceptions unless you code defensively everywhere. In fact, Poco and I actually think that Tony Hoare lowballed the cost. Null pointers have been the source of so many bugs in software over the years. This is why more modern type systems are becoming more aggressive in telling you where you have potential type and null pointer issues by making you specify when a type is allowed. The monkey type system allows us to take advantage of if splitting, where a branch expression causes the types for variables to mutate within the true and false cases. The compiler is now happy with our example, since it examines the if expression and temporarily retypes the avar argument to a number. If splitting attempts to provide the flexibility of duck typing while maintaining a healthy paranoia for null. Finding the balance between pedantic and progressive is a work in progress. Still, Monkey C is a dynamic language. We know that there is a lot that you can do with Monkey C that does not always strictly fall into our set of type system rules. If you want to explicitly turn off type checking on an individual function, this can be done by decorating the function with the type check annotation. Additionally, the type checker attempts to validate that any member fetched from a module or class is available in all the same application scopes as its caller. If the developer is confident their code is application scope safe and the type checker still complains, this check can be disabled for background and/or glance scopes. One of the goals of monkey types was to not add any runtime overhead. This allows monkey types to work on all ConnectIQ compatible products out of the gate, but it does add a cost when it comes to runtime type checking. Put simply, while at compile time, you have access to an expressive type system. At runtime, the instance of and has operators have the same limits as they had before. For cases involving polytypes of concrete types, this works just fine. However, in the case of handle candlestick, the interfaces nimble and quick are lexical types and only exist at compile time. This will cause a compiler error because instance of can only be used on concrete classes and not lexical types. In this case, we can rewrite the code to use the has operator to resolve this issue, but this isn't always possible and is a known limitation of the system. Now, we are going to move on to the second part of this breakout session, which will cover optimizations to the Monkey C build system. First, I'll discuss the optimizing code generator. Then I'll talk about our work to improve code analysis. And finally, I'll cover debug logging. An optimization pass has been introduced to the Monkey C compiler. Currently, this pass will perform several different optimizations, the first being constant folding. This is a technique where the compiler will try to recognize expressions with constants, evaluate them, and replace the expression with the evaluated value. Take this simple example, where the code calculates the number of seconds in a day. Without constant folding, all opcodes would be generated to evaluate this expression at runtime. Luckily, the compiler is capable of performing the same task with the constants that are known at compile time. Typically, you might not write such simple code, but in combination with other optimizations, constant folding can really help in improving runtime performance. Another optimization that has been introduced is static branch elimination, which is the removal of branches when the compiler can determine the branch isn't necessary. Again, take this simple example, where we know that the true case will always be the path taken at runtime. Clearly, the conditional branch is irrelevant and just wasting instructions. The compiler can rewrite this code to just invoke the do something function. The lexical-only constants removal optimization gives the compiler the ability to substitute constant lookups for constant values. This type of optimization has the potential to reduce code size and remove lots of costly runtime lookups without a developer having to sacrifice readability and the time spent explicitly doing the optimization themselves. Given this code, with the optimization disabled, there would need to be a runtime lookup for each reference of a result enum value. With the optimization enabled, these constant lookups can be done at compile time. Let's return to the example from the beginning of the breakout. Do you remember all the scopes that needed to be searched just for a couple of simple print statements? Well, this optimization allows us to completely avoid these unnecessary and expensive runtime lookups. Instead, we can simply replace the constant symbols with the constant values at compile time. Finally, we have introduced the empty function removal optimization. The compiler will map all functions that are empty to a single code section of the executable that just returns instead of generating bytecode for each empty function. Additionally, the compiler will attempt to remove empty function invocations for module functions and private class functions if those functions do not invoke another function when passed as a parameter. Now, as I mentioned previously, each of the optimizations individually might not seem very powerful. However, in combination with each other, their usefulness becomes evident. For example, you might have a debug function like this in your code to give you information as you test. Given the right debug and release level constant values, the compiler could completely remove this function and all calls to the function. Let's see how that would work. By applying the lexical-only constants removal optimization, the compiler can begin to deal entirely with constants. Next, by applying the constant folding optimization, the compiler can evaluate any expressions involving constants. This is where the branch elimination optimization can shine, by removing unnecessary branches that will never be executed. And finally, we find ourselves with an empty function. The empty function removal optimization can now completely remove the bytecode generated by this function, as well as all invocations of the function. Poco certainly thought this was pretty cool. He was pretty fundamental in the implementation of these optimizations. The -O command line option can be used to set the optimization level via the Visual Studio Code plugin's workspace settings. Currently, the levels range from 0, where there are no optimizations, 1, which is the default for a debug build and includes only basic optimizations, and 2, which is the default for a release build and includes more advanced optimizations. Optimizations can also be individually enabled and disabled at each level. Originally, the build system relied heavily on the virtual machine, transforming your code to bytecode with limited analysis in between. The compiler has been enhanced in several ways, one of those being that we want you to take advantage of monkey types, which has only improved since 2020. By default, monkey types is enabled at the gradual type check level. Additionally, the compiler will transform your source code into an intermediate representation that is used throughout different compiler passes. You might notice a folder in your output folder that contains the IR. While still operating as a dynamic language, the IR has enough information to perform the complex analysis necessary for type checking and code generation. Finally, the import keyword has been introduced, which has changed the way we analyze module prefixing. When you use the import keyword instead of the using keyword, it will bring the entire module and all classes in the module into the namespace. This allows classes in a module to be accessed without the module prefix, making for easier typing. The tool system is pretty humble. We know that you could encounter bugs with our build system. This is why we have introduced debug logging, which allows you to generate logs and provide us with a report. Command line options can be used to specify the output of your compressed log file, the level of logging that you would prefer, and the device build you would like to be logged in case you are doing a monkey barrel build. Log levels include increasingly more information about your source project. If you want to keep your project information private, limit the logging level to 1 or less. On the other hand, more verbosity will make it easier for us Garmin engineers to debug reported issues. So, in conclusion, let's summarize the breakout session. Monkey C, with its historically duck-type nature, is the language you didn't know you already knew. Monkey types is a gradual type system for the Monkey C language. Monkey types does not have runtime impact and should work with all ConnectIQ compatible devices. We hope that you can see that it's easy to use, flexible, and has a powerful array of types. On top of the type system, we have built a toolchain for optimizing your applications and providing us debug logging in case you encounter any bugs. We feel that we have set ourselves up for a bright future with the current build system, and we look forward to continuing to improve our Monkey See tools. Enjoy this last picture of Poco looking off into the sunset, waiting for me to come home, or possibly the mailman.